Hello, my chemistry friends. Today we are going to look at some properties and information about acids and bases. An acid, by definition, has to do with the number of hydrogen ions it has, or it will produce. You may remember when we learned to name acids that they all started with hydrogen. So, it's all about the hydrogens. pH is a way to measure concentration of hydrogen ions. Acids have a pH between 0 and 6. I'm going to see if I can make that bigger. All right, is this better? Bases are basically going to still be hydrogen ions, but they're going to be gobbled up at a high rate, so they aren't going to be around for long. Bases you're going to measure from 8 to 14. A neutral substance is balanced between hydrogen ions and hydroxide ions. All right, the definition of an Arrhenius acid. Arrhenius was one of the first guys to define acids, and his definition is that an Arrhenius acid has a hydrogen ion in the compound, and it will produce hydrogen ions when put into water. So if you dissolve it, it will produce hydrogen ions by dissociation. His definition of bases is that they have a hydroxide ion that is produced when they're dissolved in water. All right. Bronsted-Lowry took that a step further. If you stop and think about hydrogen, hydrogen has one proton. Most hydrogens have a molar mass of 1, meaning they don't have any neutrons. And a hydrogen is going to have 1 electron whizzing around. Okay? If we're talking about hydrogen ions, a hydrogen ion, that electron has gone away, and we've been left with a positively charged ion that is made of 1 proton. So we can call a hydrogen ion basically a proton. And that is how Bronsted-Lowry and Lowry defined acids. They donate protons. In other words, hydrogen ions. And a base, this definition is very different. A base can accept protons, aka hydrogen ions. All right, some of the properties. Acids tend to have a sour taste. Something you probably did in grade school. You did a litmus test. It turns litmus red, and they will conduct electricity. Bases have a bitter taste. They turn litmus blue, but they also will conduct electricity. Okay, what does that mean to conduct electricity? Well, if you put 2 wires that are connected to a light and a battery into water, if it is an electrolyte, the electrical charge will move through the substance and light up the light. So an electrolyte is something that will allow electricity to be conducted. And it does this by dissociation. We talked about dissociation when we talked about solubility. Dissociation occurs when you have something and you put it into water and the ions completely separate. A strong electrolyte will completely separate. It will go through dissociation. Okay? We have 6 strong acids that you need to know. Hydrochloric acid, nitric acid, sulfuric acid are the 3 most common. Also included in there is bromic acid, iodic acid, and perchloric acid. And sometimes chloric acid is included as well. I've seen that. Strong bases are going to have the OH in them. So we have lithium hydroxide, potassium hydroxide, sodium hydroxide, rubidium hydroxide, cesium hydroxide, barium hydroxide, calcium hydroxide, and what am I missing? Strontium hydroxide. Now, which element from the second family is not listed in there as a strong base? That would be magnesium. If you take out your solubility charts and you look at solubility for hydroxides, hydroxides are generally insoluble except for the big 3 2As. Calcium hydroxide, strontium hydroxide, barium hydroxide. Magnesium hydroxide is insoluble. If it's insoluble, it's not going to dissociate in water, and that's why magnesium hydroxide is not on this list. A weak electrolyte is not going to dissociate completely. Something like vinegar. If you put vinegar into water, some of the hydrogen ions will come loose, but most of them will not. So we actually put 2 arrows into that equation, and what those arrows show that while some of them are dissociating, really most of them do not. And that's a weak electrolyte. It can't conduct electricity as well. Vinegar, hydrogen fluoride. That's in the POGIL in your notes that we'll talk about later this week. Carbonic acid, which is in soda pop. As far as weak bases go, any of the Bronsted-Lowry bases, other than the hydroxides, are going to be weak because they're not going to have that hydroxide. So ammonia, if you have NH2, that can pick up another hydrogen. All right, so let's turn to the back side. If we're talking about acids, we can write it as H+. We know that that's a hydrogen that has lost an electron. But water will pick up that hydrogen and become what we call a hydronium ion. This is a polyatomic ion, just like the polyatomic ions we learned about when we did naming. Hydronium is the other positively charged polyatomic ion that you'll see. And we have, it forms H3O with a positive on it. Okay? Let's go back to this idea of dissociation. If you have water molecules, anytime you have water molecules, some of those water molecules are going to dissociate into hydrogen ions, and some will dissociate into hydroxide ions. Okay? They're going to be equal. And that's going to help us with our discussion of determining pH. All right? If we know the hydronium ion concentration and we know the hydroxide ion concentration, the 2 of those multiplied together comes out to be 1 times 10 to the negative 14th. If it is water, it's going to be neutral, and you're going to have 1 times 10 to the negative 7th molarity of hydrogen ions, and 1 times 10 to the negative 7th molarity of hydroxide ions. Multiply those together, and you get 1 times 10 to the negative 14th. This is often called the equilibrium constant of water. All right. Now, we can use this information to determine pH. pH, is a quantitative scale that describes the concentration of the hydrogen ions. The acidity of a solution is expressed in terms of molarity. If you have a hydrogen ion inside brackets, that's talking about the concentration of the hydrogen ions. All right. So, where'd it go? What this is going to tell us, if we know the hydrogen ion concentration, we can come up with a hydroxide ion concentration. If we're talking about water, it's going to be 1 times 10 to the negative 7th, the hydrogen ion concentration is, and the hydroxide ion is also going to be 1 times 10 to the negative 7th. All right, what does this mean? Well, if we want to figure out a solution, if we know that we can multiply hydrogen ion concentration times hydroxide ion concentration, and we get 1 times 10 to the negative 14th, we can just do a little algebra and come up with whatever we don't know. For instance, in this first one, we know the hydroxide concentration. So if we take 1 times 10 to the negative 14th and divide it by that hydroxide ion concentration, we're going to end up with 1 times 10 to the negative 8th. Okay? The second one, well, let's go to the third one. The third one, we don't have the hydroxide ion concentration. So again, we're going to take 1 times 10 to the negative 14th, divide it by 2 times 10 to the negative 5th. If you don't believe me, get your calculator out, but I will tell you the answer is 10 to the negative 10th. The next one, again, 1 times 10 to the negative 14th divided by 1 times 10 to the negative 12th, we end up with 1 times 10 to the negative 2nd. The next one, 1 times 10 to the negative 14th divided by 7.4 times 10 to the negative 3rd, we end up with 1.35 times 10 to the negative 12th. And the last one, if we divide them, 1 times 0.8 times 10 to the negative 13th. Now, pH. Tricky little devil here. That P actually stands for the negative log. The H stands for the hydrogen ion concentration. So if we know the hydrogen ion concentration, which we just calculated right there, we should be able to use calculations and a calculator and figure that out. All right, so here's a calculator. We just calculated that the hydrogen ion concentration for the first line was 1 times 10 to the negative 8th. So if I take a negative log of 1 times 10 to the negative 8th, I get a pH of 8. The next one, if I take the negative log of 2 times 10 to the negative 5th, we better erase all that. Negative log 2 times 10 to the negative 5th, we get 4.69, which I will round to 4.7. The next one, 1 times 10 to the negative 12th, we're going to do negative log 1 exponent negative 12, and we get 12. The next one, 1.35 times 10 to the negative 12. $11.9. And finally, the 5.6 times 10 to the negative second. If we take the negative log of that, we get 1.25, which I'm going to round to 1.3. All right. We know that anything that's above a 7 is basic, so an 8 is basic. 4.7 is below 7, so that's an acid. 12 is above 7, so that's a base. 11.9 is going to be a base. 1.3 will be an acid. Now, this is one of those questions that always boggles my mind because I don't remember back that far, but you guys all know that logs are the same thing as 10 to an exponent, right? All right, so we're going to see if we can do this. On the worksheet, we have a pH given with no hydrogen ion concentrations, but we should be able to plug that in if we know that 10, okay, that didn't work. If I put in a -3, that gives us a concentration of 0.001. And that is the concentration for the hydrogen ions. Now, what do you do if you want to convert it to hydroxide? We're going to take 1 times 10 to the 14th divided by 0.001, and we end up with 1 times 10 to the negative 11th. Now, there is a worksheet in your packet that is much better at explaining this that we will do together next week. All right, thank you very much for learning about acids and bases.